Hi everyone! In today's video, we're going to be going over forces in 2 dimensions and also practice problems with forces in 2 dimensions. So let's go back to 2-dimensional topics we learned before, such as kinematics in 2 dimensions or vector addition and subtraction. When we have forces in 2 dimensions, it basically means that we have forces acting both in the y component and in the x component. This can sometimes mean that forces can be acting at an angle. So, for example, if this was a wagon, someone could be pulling this wagon with a certain force at an angle of like 45 degrees above the horizontal. And the way that we solve these problems is we break them up into the x component and the y component. And we find the sum of all forces in both those components. So let's go over an example problem together where we go over how to do this. Okay, here's our example problem. A 10-kilogram box is being pulled across the table to the right with a force of 50 newtons 30 degrees above the horizontal at a constant speed. So before we go to the parts of the problem, we need to make sure that we understand what constant speed means. Constant speed means that there's no acceleration and that the net force in the y and x direction are 0. So F net x should be 0 and F net y should equal to 0. Okay, so the first part is asking us to calculate the normal force. Again, before we go into this, let's draw a free body diagram. So in part B, it asks for the coefficient of friction, so we know that there is a friction force acting on this box in the opposite direction. We have the force of gravity, mg, the normal force, the force of 50 newtons, which is 30 degrees above the horizontal, and then we have our force of friction. So in this case, our normal force wouldn't equal to mg because there is another force acting in the y component. What we have to do is figure out all the y components by figuring out the F net in the y. Taking up to be positive and down to be negative, let's calculate the y component of our force. And if you remember from our vector video, the way we do that is we calculate the net vector of a force, which is 50 newtons, times the sine of our angle, which is sine 30, and that's going to give us 25 newtons. Okay, so we know that our normal force plus our 25 newtons, because both of these are pointing up, meaning this is in the positive plane, minus our weight, mg, is supposed to be equal to 0 because our F net y and F net x are 0, meaning that we are at a constant speed, no acceleration. So we have to solve for what our normal force is. We already know what our mg is, so we can simply rearrange our equation as n equals 2m, which is 10 kilograms, times acceleration 9.8 minus 25, and that should give us our normal force. And this gives us 73 newtons for our normal force. And this is something important to keep in mind because sometimes some people always assume that normal force is equal to the weight of the box, which is not true because sometimes we have other forces acting in the vertical direction. Okay, now we know our normal force. And part B is asking us to calculate the coefficient of friction. Before we do that, we have to figure out what our friction force is by finding our F net in our x plane. And we know that is supposed to be equal to 0. So let's calculate the x component of our force, which is going to be 50 times cosine of our angle, and that is going to give us 43.30 newtons. So if we take right to be positive and left to be negative, this is going to be our F net x equation. 43.30 minus the force of friction is equal to 0. And it's equal to 0 because once again we're moving at a constant speed, meaning there's no acceleration. Rearranging for friction, we get friction as 43.30 newtons. Okay, now that we have our friction, we know that friction is equal to coefficient of the kinetic friction, since our box is moving, times our normal force. Since we have our friction and we have our normal force, this is going to be our equation. Mu k times our normal force of 73. And rearranging for our coefficient by dividing, we should get 43.3 divided by 73, telling us that our equation is equal to about 0.6. So that is the coefficient of our kinetic friction. Okay, so completing this first problem, I hope you noticed that we took a look at the forces acting in both the y and x components separately. And we knew to set them equal to 0 because it was at a constant speed. Sometimes you can set it equal to ma if it's experiencing acceleration or if the net force is not 0. So let's go over another common example, which is the incline. And before we go over how to do the incline problems, let's go over drawing the free body diagram for an incline. Okay, one of the most difficult things in two-dimensional dynamics is the inclined plane, because drawing the free body diagram is where most students get confused. So there are two important things to keep in mind when drawing the normal force and the force of gravity. So normal force, despite the situation, is always perpendicular to the surface. The force of gravity, despite the situation, is always perpendicular to, let's say, like the planet. In this case, Earth. Okay, so knowing this, taking our box to have a center of mass, the incline right here, is our surface. So our normal force has to be perpendicular to it, like so. This area is our planet, the surface of our planet, or Earth, and that means our gravitational force or weight has to be perpendicular to it, like so. So that's where many people get confused. And let's say that this plane has friction. So if our box is sliding, let's say, to the right or down the hill, we will have a force of friction left. And friction is always in the opposite direction of motion. So if the box is sliding down the hill at this diagonal kind of angle, then our friction should be going in that angle. And that is why it's exactly opposite and parallel to the surface. Okay, so now that we have a free body diagram, how are we going to break up our forces into components? What should we do? Where should we take our y direction? And where should we take our x direction? So on an inclined plane, we find the easiest version for certain problems, depending on which, is to take the y direction perpendicular to the plane and the x direction parallel to the plane. It depends on the problem because sometimes the y direction doesn't have to be perpendicular. It can be angled such that the y direction is perpendicular or parallel with the weight rather than the normal force. Okay, so now we have our coordinate plane in which we've defined the y direction to be parallel to the normal force and the x direction to be parallel to the surface of the incline. So how do we break up our forces into components, especially the weight? And first let me redraw this so it's better to see. Our friction force and then our weight or gravitational force. Okay, so here we see that our inclined plane is 30 degrees above the horizontal. So if we know about triangles, the geometry of triangles, we can imagine this to be our right-angled triangle here. Because we know that our weight is perpendicular to the surface of the earth or the bottom of this plane of this incline, and that tells us that this is a right angle and the acute angle here is 30 degrees. That means the angle between the x-plane and our weight should be 60 degrees because the angles in a triangle are 180. And that tells us to use that 60-degree angle to break up our weight component into the y and x coordinates. So this topic is a little bit difficult because there are so many different, we're shifting our entire coordinate plane to match the inclined plane. So let's go over a practice problem. Okay, so here are practice problems. Our problem explores all of the 2D stuff that we learned, and also what's special about it is the forces are not balanced in this case. Our box is accelerating. So a box of mass 47 kilograms is sliding down a rough surface incline that makes an angle of 34 degrees with the horizontal. The coefficient of kinetic friction between the box and the surface is 0.28. Find the value of the normal force and the kinetic friction force, and also find the acceleration of the box. Okay, the first step we do is draw a free body diagram. That is the first step in any dynamic problem. So, as we learned, gravity is perpendicular to the surface, so this is our mg. Normal force is perpendicular to the surface of the plane, so gravity was perpendicular to the surface of the planet, or the Earth in this case, and normal force is perpendicular to the surface of the plane. And since it gives us a coefficient of kinetic friction, we say that there is a friction acting in the opposite direction of the sliding movement, and it's sliding down the surface. So a friction would be parallel going left. Okay, so now we have to draw our forces on an x and y coordinate plane. And you can either draw this directly on your free body diagram, or so I always draw it to the side so that I don't get too cluttered in my free body diagram. Okay, so this is our y and this is our x. I'm moving my coordinate plane in such a way that my normal force is directly lined up with the y. My friction force is directly lined up with the x, and my mg is at an angle. And in order to find this angle, we know that our surface has an incline of 34 degrees above the horizontal, and our mg is 90 degrees because it's perpendicular to the surface of the earth. And so if we imagine this as one triangle, all we have to do is 180 minus 90 minus 34, and that gives us an angle of 56. So our angle against the x-plane for our gravitational force is 56 degrees. Part A is asking us to find the normal force and then the kinetic friction force. And in order to find kinetic friction, we have to find normal force first. So you may be wondering, how can we find the normal force if all we have is the gravitational force? We don't have the frictional force or anything else. So I want you to take notice. If our y-plane is in this direction, our box isn't flying up in that direction. It's not moving in that direction. It's stationary in that plane. This tells us that if our y direction is in this plane, I'm going to use a marker. I can't show you, but in this plane, that means our F net y has to be equal to 0, or that it is balanced. And that is because we can see it's not accelerating in that chosen plane. So, let's take a look at what's in our y direction. We know if we take, again, positive upwards, so let's take a look at these standards here. If we take upwards to be positive, it's going to be normal force minus the y component of our gravitational force, which is going to be mg sine of our theta. So now rearranging for n, since we know this is once again equal to 0, n is equal to mg sine of our theta, and in this case we know our theta is 56. So let's plug this all in. We know our mass is 47. We know our gravitational acceleration is 9.8, and we know our theta is 56 degrees. So 47 times 9.8 times the sine of 56 degrees gives us a normal force of 381.85 newtons. In order to find the kinetic friction force, we can't do a force net equation. The reason for that is that we don't know what our acceleration is. But we do know the friction equation and the coefficient. We know that the kinetic friction equation is equal to the coefficient of kinetic friction times our normal force. The good thing is we have both of those. That means that our kinetic friction is equal to 0.28, our coefficient, times our normal force of 381.85. So plugging this into our calculator, we get a kinetic friction of 106.92 newtons. Okay, now that we have finished part A, we have to figure out the acceleration of the box. We already know that on our y plane we are balanced because our box is not flying off of the incline, it's sliding down the incline, directed in the x direction, because that is what we defined our coordinate plane as. So, we know that F net is equal to ma. So let's take a look at our F net in the x direction. We know that if we take right to be positive, mg cosine theta is going to be the force acting to the right in the x direction, and our friction force is going to be what's acting left. Since we don't know if this is balanced, all we can say is that this is equal to our mass times acceleration. In order to solve for acceleration, we simply divide both sides by m, and this tells us that acceleration is equal to mg cosine theta minus the force of friction divided by our mass again. So plugging in our numbers, we will get m, which is 47 kilograms times 9.8, times cosine of our angle, which is 56, minus 106, well, I can't fit this in, but you know the force of friction is right here, minus the force of friction divided by your mass again, which is 47 kilograms. So let's plug this into our calculator. 47 times 9.8 times the cosine of 56 to give us the x component, minus the force of friction, which is 106.92, and then divided by our mass, which is 47 kilograms, gives us an acceleration of 3.205 meters per second squared. Okay, I hope this video helped you all, and below in the description I have linked a practice problem PDF that includes 2D dynamic problems. Some of the problems may be more advanced, but we will go over how to do those in the next videos. Thank you for watching!